Hello, everybody. My name is Kanty Milczek, and today I'm doing a deep talk on the topic called LLMs and WinRAR. What do they have in common? What do they have in common indeed? But first, I need someone to tell me if you can hear me just right. Should I be a little bit louder, a little bit quieter, or whatnot? Okay, if it's perfect, then let's get right to it, I suppose. Okay, so a quick agenda first. First, to talk about this, we're going to have to define what a language model is and what data compression is, of course. Then we'll find that compression actually makes files bigger. We can prove that scientifically. And then we'll talk about why I'm lying and actually compression does make files smaller. We'll examine why. We'll pretend that everything is simple, but in fact it is absolutely not. And then we'll go straight to the topic of what is actually common between LLMs and compression algorithms. So let's go. So firstly, why are we talking about this even? And we have a quote from my evil twin right here that says, LLMs take a lot of disk space. WinRAR compresses data and saves space. So because of this, those solutions excel when used together. This is, of course, utter nonsense. If you compress LLM weights with WinRAR, you're likely going to not gain anything at all. I wouldn't count on it. Maybe you'll shave off 1% or 2%, but I don't even know. Likely not even that. So again, what is a language model? A language model is pretty much any model that describes a language, logical, right? So we're going to be talking about a specific type of language models, so the continuation models. Those models say, if we have some history of text, what will be the continuation of this text, right? And because of this, and because of most languages are actually very fuzzy and undefined, then we're going to use probabilities. So instead of just saying, oh, the continuation is like this, we're saying, oh, the continuation might be this with this probability. It might be that with that probability, and it might be something else with some other probability. And we're not talking about tokens right now, but we're simplifying stuff for now. Let me just mention here that even though I said the text so far, which implies going from left to right, some of you might think stuff like, oh, but what about BERT? BERT doesn't predict what's next. BERT predicts what's inside. Pretty much any model that takes some of the input and predicts probabilities for the rest of the input applies here just as well. Okay, and we're done with LLMs. Perfect. So let's just go with data compression. What is data compression? Everyone, I hope, has used extensively data compression in their lives. I remember like 10 years ago, everything was zipped, RAR'd, or 7-zipped, at least on Windows, tar-gzipped on Linux. And what I knew about compression back then was that the compression algorithm identifies some patterns that repeat, and then kind of codes it in a shorter way. The most basic algorithm compression algorithm you could envision is an algorithm that takes the input, and if it sees a fragment that was already there, then it just codes, okay, just repeat whatever was before at those indices, and it works. But of course, the actual compression algorithms are more involved. And for now, we can just pretend that some kind of magic happens inside them. We don't even think about it really, but we've all seen that a zip file is usually smaller than its contents. So it works. And also, probably some of you have noticed that, especially if you were there 10 years ago, that if you download an MP3 file, for example, or a zip with MP3 files, there was pretty much no savings through using a compression algorithms for some reason. For now, we're just gonna say it's for some reason, and that's it. Okay, so now let's do a thought experiment to end this section. What happens if we generated absolutely all possible files of a certain size? In this case, we're going to ask about 5 megabytes. There's a lot of those possible files, but let's pretend we were somehow able to generate them. We had infinite time, we had infinite disk space, and yeah, we just succeeded. So my question is, what do you think is the average size of the file after zipping this way? Who can guess? If someone can guess, just put an answer in chat. I need any answer to continue. Okay. I'm getting some answers in here. And so far, I think all of those answers are wrong. I do not know how to interpret answers like 1% or 1.7 because I do not know what they mean. Maybe they are better than the other answers, but okay, no. It's not going to be 1.7 megabytes. The answer is going to be at least 5 megabytes. And if this answer confuses you, then let's examine this a little bit closer. But first, let's go to the next section called Compression Makes Files Bigger. And this was my impression back when I was a competitive programmer. The name of the game was always pessimistic complexity, pessimistic space complexity, time complexity, pessimistic case solution size or whatnot, because we wanted our programs to work always and work well. So what I discovered was a very, very simple thing. If each archive starts with some signature, some header that tells the system that it's an archive, for example, zip files start with the letters PK. They are binary files, but the bytes are actually the letters PK. And that means that if we want to code all those 5 megabytes files, then each of the resulting archives has to start with P and K, right? So we have at least 2 bytes added onto each file, which does nothing absolutely. And then each of those archives, of course, needs to be different from the other archives. Obviously, it needs to be different. So if it needs to be, because otherwise we would have 2 files, 2 zip files that decompress or extract into different things, but the file itself is the same. It makes no sense. So that means that to encode a set of files, a set of all the files of a certain size, we will need at least as many different files as we want to encode as the compressed archives, and each of those starts with PK. So to encode 5 megabyte files, we would need at least 5 megabyte files plus 2 bytes, all of them, to do so. So the average size of the archive needs to be bigger than 5 megabytes. It just has to. There is no other way. So after doing this, maybe some of you have done the similar thought process as the 10 years younger me did, or 15 years younger at this point, I suppose. Time flies. You have made the same proof. Now we know that compression is a lie. Compression makes files bigger, and we know we cannot really save space, right? Okay, we know that we've been using compression algorithms. We've been using zip files, targz files, or whatnot, and we know that it makes files smaller. So the question is, where is the lie? Where have I lied to you so far? And the answer to where I have lied lies in the word average. I was always talking about the average size of a file, but average is a very relative term, because if I generate all the possible files, then we can say, yeah, sure, the average is just the average of all of those files. But I do not actually in life generate all the possible files, right? I would never. Similarly, some of the files have value, some of the files carry some information, others are just utter gibberish. And if I take all the files of a certain size, all the possible files, then of course, most of that will be absolutely unusable gibberish. And we do not care about compressing unusable gibberish, right? So now let's enter a completely different topic. Let's talk about my favorite and maybe one of the simplest compression algorithms, which is Huffman coding. Okay, let's do another thought experiment. We need to compress a sequence of class labels for a classification problems. Those labels are very known to anyone who's ever read an ImageNet paper. So let's use those: cat, dog, cow, and I suppose, I don't know if banana was there, but I added it nevertheless. Okay, and if we have a sequence, just by looking at this sequence, you can tell that there's a lot of cats in there. And if we see a big disparity between the counts or the ratios or the frequency of each element, maybe we'll be able to leverage it down the line. So just in case, I have put the frequencies, or I call it ratios, but English is my second language, so that happens. So we have those for labels and their frequencies. But first, let's do any compression at all. Okay, firstly, if we use 2-bit labels and encode each cat as 0, 0, let's say, I mean bits, not characters, of course. 0, 1 for dog, 1, 0 for cow, 1, 1 for banana. Then, of course, we no longer have to save the string. Now we only use 2 bits for each label. This comes down to 4 labels per byte. So this is already very, very good compression. And my question to you is, can we do better? Can someone propose a set of labels, of those 2-bit labels for the labels, that gives us even better compression? Okay, Irek says yes, encode cat with 1 bit. Okay, let's try to do just that. Thank you for the suggestion, Irek. Thank you, Mateusz. Let's assign those codes. Those codes are actually of different lengths, but one thing you can notice about them is you cannot really mistake them. For example, if we try to encode cat as 0 and dog as 0, 1, then we do not know what 0, 1 means. Is it a cat and something else, or is it a dog? We do not know. But in the case of those labels I put here, there is no risk of confusion. And because of that, now we have a code which is variable length. It is asymmetrical, so to speak. And the cat gets all the attention with the 0 at the beginning. And it turns out that the average size of a label is 1.25. So even though we've said that this compression to 2 bits is already very good, actually we can get much, much better, and we improved our result by almost half. So good for us. So what we need to remember for now is that we need to assign less space, as in coding space, or less space in the compressed file, to something that is more probable. And if we do that right, then we are successfully compressing. Okay, so you have probably noticed what I said, that we want things that are more probable to be encoded with shorter codes. So that word prediction or that word probability should tell us where I'm going, that I'm going into language models after all. So we know that if something is more common, then we can encode it shorter or should encode it shorter. Some things are less common, and we can put them longer, but we know that they will happen less often. So the compression is there. But in the previous example, we used constant measure of commonness, right? There was frequency, and that was it. And that was it for Huffman coding, at least. But this is not what we have to do. We are not resigned to just using frequency as the only source of truth of what is probable. Because if an LLM sees, let's say, the first 1,000 tokens in a sequence, the first 10,000 tokens in a sequence, whatever, and tells us that the next token would be cat, dog, cow, and banana with those probabilities, then we could Huffman code that next token based on the probabilities from the LLM. And then we have another token into the LLM. We have new probabilities for new tokens, and we can encode all over again. Because why wouldn't we? Well, maybe some of you would say we wouldn't do that because it will be very, very hard to decompress. So let's talk about how to extract something from an archive that we've just created this way by Huffman coding the LLM output. Okay, we have a sequence, of course, of codes, and this is absolutely useless if we don't have the LLM, right? Because the LLM, we need to know what is the most probable token, what is the number of tokens, what is the distribution of next tokens, to even know how to compress it or how to decompress it in this case. But I said it's useless without the LLM. So let's use the LLM, the very same LLM. It is actually crucial that we use the very same LLM. So let's say we've decompressed the sequence so far. So if we decompress the sequence so far, then we have the exact same input that we had while compressing, right? So we can take the probabilities, we can calculate the Huffman coding for those probabilities that we have here, and from that we know what we actually encoded with our Huffman code. So if we write it deterministically, we can do it both ways. So if we know how we would encode tokens and we know what we've encoded, then we know what we encoded. That's pretty much it. So we've just designed a LLM-centric, LLM-backed compression algorithm, which is pretty cool, I suppose. So let's now talk about actual real world and how those things are actually done and actually coded. So firstly, probably I've asked before in this very talk the question, can we do better? And again, some of you might wonder, can we do better? And I'm answering right now, yes, of course we can do better, because so far we've used the minimum of 1 bit per token, right? Because even the most probable token, even if it's 100% probable, probably, well, not 100, but let's say 99.9% probable, we still needed at least 1 bit to encode it, right? That's Huffman coding. But it doesn't have to be this way. We can actually use less than 1 bit to encode the next token or something very, very probable. This is if this is very hard for you to grasp at the moment, it used to be very hard to grasp for me. Think about it this way: if you knew the next three tokens, for example, with probabilities 99.9, 99.9, and 99.9, then the whole probability of the sequence of the 3 next tokens is already closer to 99.5, right? So it's completely reasonable to assign 1 bit to a sequence of 3 tokens. And it would still work. By the way, if you think this is it, no, this is still not it. This is still not the best solution. The best solutions are based on Shannon's entropy and from the information theory, and they are called sometimes entropy coding. But if you Google entropy coding, they'll tell you about entropy coding with constant frequencies, just like we did Huffman coding originally. So no, this is not yet what we're looking for. There's also arithmetic coding, which is one of the ways to implement entropy coding. And similarly, it is not actually, it is, if you go into Google, they will tell you about arithmetic coding for constant probabilities. So the most ideologically relevant algorithm that is already available is or at least the most ideologically relevant algorithm would be context adaptive binary arithmetic coding, which is used in the modern video codecs, for example. And context adaptive means that depending on the context, it actually updates the probabilities of what it expects, which is what we do here. But for some reason, this is not the standard if you look for actual algorithms, but rather a recent development. Well, not exactly a recent development overall in compression, but recent development when it comes to algorithms that are easily Googleable and relevant to what we're talking about. So some of you might think that I started by saying, or at least suggested it, that compression and language modeling is pretty much the same. And you might think that you do not actually need a language model to zip or unzip files. And my answer here is you do need the zip or unzip program to zip or unzip files. And it turns out that actually the zip program or the unzip program has a lot of heuristics and algorithms that define what is probable as the next part of the archive. So you do actually have a quote unquote language model inside the program. And it's not that far of a stretch to think that maybe one day the zip program, or maybe not zip program, but tar.llm, let's say, will be 20 gigabytes in size, and you'll need that to compress and decompress files. Maybe that is the future, but the compression will be crazy good at that point. Also, if you're again asking the question that I've asked before, which was, can we do better? In this case, the answer is no, we cannot really do better. I mean, at least for a certain language model or a certain just model of the input. Because if we have a model of the input with proper or as close to the real probabilities as we can go, then the properly implemented arithmetic coding, of course, with context awareness, will be the optimal way to compress something, and that is just period. You cannot do better. Information theory says you can't do better because you need at least as much bits of information as the entropy of the input. But I wanted to avoid information theory, so let's not dwell on this any further. Okay, and this is pretty much it before the time for the questions. So let's just very, very quickly think about what we've learned today and how we can use it. Well, firstly, we've learned that LLMs let us create more efficient compression methods. And the better, of course, the language model in the end, the better the compression will be. It is also extremely unlikely that you'll actually use those facts and the fact about the duality of the compression and language modeling in an actual work project. But still, I hope that we've gained some understanding into how things are done, and at some point this will spring up and will be the big winners who know all the intricacies of different kinds of computer science. And my personal note is that information theory is just very, very cool. And the deeper you dig into information theory, pretty much the better is your understanding, not just of mathematics, but of data science, of programming as well. And in my opinion, also about some real life processes, if you're okay to think about everything in terms of math. And this is all from me for this deep talk, and I'm very happy to take any questions.